So in this class, we're going to talk about how we actually can say what may happen in the future. We've spoken all throughout the course about all the different processes which impact the climate. But if we want to estimate what may happen in the future, especially for policymakers, if we want to plan for the future, we need to use computer models. Computer models are a crystal ball where we can look into the future and see what may happen in the future if we do A, B, C, and if we don't do those things, what may happen. And during the course, we've spoken about different parts of this image we see here. We've spoken about the sun and the sun's rays and how they get absorbed in the atmosphere by gases, by particles reflected off clouds, how clouds are formed, the impact of clouds on the radiation balance. We spoke in the last lesson about volcanoes and volcanic aerosols. We spoke about the biosphere, the plants, the oceans, the sea ice, the land ice. All of these factors we see in this image and more need to be simulated in models, which means we have to write code to explain them. We need to write the physical equations, chemical equations. Everything has to be put into code, into a computer, and run in order to try to simulate the climate. An extremely difficult job, and we have groups around the globe of maybe hundreds of scientists which work on individual models, trying to improve them all the time, to improve the physics of the models, of the numerical schemes we use in the model. How do we solve all these equations simultaneously? And we need huge supercomputers to run these models. Now, these models have developed over the last decades, and there's been a progression from the very simplest models in the 1970s, where we basically just looked at the atmosphere, but we didn't really have an ocean, we didn't have plants, we didn't have anything else. We then, in the 1980s, we added a land surface model. Land surface means that we have some interaction with the plants or what we have on the ground, the soils, water which gets taken up when it rains in the ground. In the 1990s, we added ocean models. Until these later versions, we had offline models. We had models which we would run by themselves, like the ocean models or the sulfur cycle models, and then the output from those models were put in to the larger climate models. And as we get more and better computers, we've started to add more and more complexity to the large climate models. You can see by the early 2000s, we have carbon cycle, non-sulfate aerosols, sulfate aerosols, which are in the stratosphere. And now we have also atmospheric chemistry. And all of these have to speak to each other. As we spoke about in the volcanic eruptions, when you have eruption of sulfur dioxide, this has to react to produce the droplets. The droplets then reflect the sunlight, they impact the albedo, they get transported by the winds around the planet. So all of these different modules, these different circles here have to speak to each other. They have to be coupled and interact with each other. And we have to solve all of these equations every time step, which may be, say, every 15 minutes. We want to recalculate the winds and the clouds and the rainfall. And this has to be done on a global scale. And we have to do this for 100 of the model years if we want to predict what is going to happen in, say, 100 years. So extremely complex and difficult. And today, instead of calling them climate models, we even call them Earth system models, because we're looking at the whole system from the sun down through the atmosphere to the oceans, the biosphere, the cryosphere, the lithosphere, again, the volcanoes. All of these have to work together when we're calculating the climate. And one of the impetuses which is pushing these models development forward are the reports of the IPCC, which come out every 5 to 7 years. And we can see again schematically how these models have increased in complexity with time, from the mid-1970s, where we basically just had CO2 going into the atmosphere, and we had no clouds, but when the atmosphere reached saturation, it would produce rain. Later on in the mid-1980s, we started to have clouds, which then affect the albedo. We have also land surface. We have something related to the ice. In the first assessment, the FAR is the first assessment report of the IPCC, the second assessment, SAR, third, and then AR4 is the fourth. Each one, we have more and more complexity into these models to try to simulate the planet in much more detail and in a much better way. The resolution has also increased dramatically with time. We can again see the first, second, third assessment report, and AR4 is the fourth. We're now up to the sixth assessment report. And you can see in the first one in 1990, the size of the grid boxes in the model, the size of the pixels was about 500 kilometers by 500 kilometers. Now we're less than, say, 1 degree, which is around about 100 kilometers. You can see for the AR4, we can start to see the topography in Europe. You can start to see England and the Alps, whereas in the first report, you wouldn't really know where we're looking on the planet because of the coarse spatial resolution. So the resolution has increased dramatically over time, but when you increase resolution, you also increase the computing time needed to solve all the equations, and the computing time needed increases inversely with the cube of the horizontal resolution. In other words, if we double the spatial resolution, we have to have 8 times more computing power to solve all the equations in the same amount of time. But we've increased the computers now. Every year we're having better, stronger computers, and so we've been able to increase the resolution, but still we're around about half a degree, which is 50 by 50 kilometers, and many things in nature occur at scales which are smaller than 50 kilometers. If we talk about plants, if we talk about clouds forming, and therefore we still need to make a lot of assumptions about what's happening in the small scales below the grid size. Today, people are talking about quantum computing in the future, which may give us another jump forward in the resolution we can get to because of the speed that these models may be able to solve the equations. And so in the future, we may have climate models globally which can actually solve all of these equations for all the different parameters at even 1 kilometer resolution, but we're still not there. So again, to solve the climate and to simulate what happens in the future, we have to look on a global scale. We have to take the world, break it up into these little boxes we call grid boxes. We have to define what's the size of these grid boxes, the longitude, the latitude boxes. We have to also simulate with altitude. We have to divide the atmosphere by layers. How many layers do we want? Do we want 20 layers, 50 layers, 100 layers? Same in the oceans. We have to simulate the currents in the ocean, the Gulf Stream that is taking heat to the northern latitudes. How many layers in the ocean? All of these have to be decided before we start to run the model, and all of these boxes have to be interconnected, and all of the processes in each individual boxes, like we can see here in the diagram, have to be interlinked. So for every time step, we have to calculate the radiation balance, what's the radiation coming in, what's going out, the clouds that are forming, is rain forming in that box, the ocean currents, the absorption of carbon dioxide by the ocean, by the plants. In every box on the globe has to be done at every time step. So this is a huge challenge which has been done and gets improved, but we're still far away from having perfect models to predict the climate, both in the past and in the future.